started.
Great. Okay, well, hey, welcome everybody. My name is Tero Vuorenmaa from Robot Expert, and I'm hosting today's webinar. We will have an interesting presentation about 5G drone projects. First, we will look at what is actually 5G drones project and what was our goals, and then we get deeper into the use cases. Didn't want to stay there once more. There we go. So what are the use cases what we used in the project, and then we will have a short introduction of different 5G networks and also architecture what we develop to collect the data, and finally we will look at trials and lessons learned. So for the speakers, I try to kind of take care that we will be on time and on schedule. So I will lift my hands when you have 2 minutes left, and I will then open my mic to disturb you if you are gonna be doing too long presentations. But yeah. So first, Jussi Haapola from University of Oulu was promising to give a short introduction about 5G drones. So go ahead.
Okay, thank you. I'll just share my screen. And hope you can see. So my name is Jussi Haapola. I'm from University of Oulu, and I'm the project coordinator for 5G drones. So 5G drones is a project. It's ICT 19 call, which started pretty much 42 months ago, and it will end at the end of this month. So 3.5 years of duration with approximately 30 million euros of budget and 21 partners at the moment. So the motivation for this entire work was that unmanned aerial vehicles basically have attracted a huge interest in civilian and commercial applications. The technology, regulatory changes, and reduced cost of sensory components and onboard control units have made it more attractive to actually try them out in a commercial environment and in a real environment. Of course, now that the regulations have changed back and forth, or are changing even like day after tomorrow, so it's posed some challenges in implementation of this project, because we have always had to bear in mind what are the current regulations and also what are the regulations to come by the end of the project and what are the expectations. So one of the key motivations also is to, in order to enable a wide adoption of UAVs, it's basically vital to build a reliable wireless network that supports massive use of them. So continuing the project overview, it builds on a specific number of pillars. So firstly, we want to drive the UAV verticals, so the UAV area itself entirely, and 5G networks to a common win-win position. And that drives to the main purpose of this project, to validate the 5G KPIs to support several UAV use cases via trials using 5G shared infrastructure, as well as validating the UAV KPIs in such a fashion that the 5G is a key element to actually being able to realize them. So the project has been built on top of so-called 5G facilities that have been provided by ICT 17 framework, which are 5Genesis platform and 5GE platform in 2 different projects spread around Europe in multiple locations. In addition to that, we have 2 additional sites, the Aalto-X network in Espoo, Helsinki, Finland, and also University of Oulu 5G test network in Oulu, Finland. So the project features network slicing as a key component to simultaneously run UAV services on the same 5G infrastructure. But that's not all. Basically, in order to enable this win-win position, the project has built a software layer to automate the run of trials. So all the way starting from planning of a trial to the execution and post-processing of the trial. And the project also enables abstracting the low-level details of different 5G infrastructures so they can be effectively utilized by UAV operators and use case users that don't have specific knowledge or information of 5G technology itself. So the key questions for the project, what we have tried to address in this project. So what are the missing components currently? What components need to be improved? How can we actually enable UAV verticals to run the tests? So in that way, we need to abstract the APIs in each of the facilities. And how can we do it in that we can abstract APIs of multiple facilities at the same time. And then how to test the performance of the ICT-17 facilities, and then how to build a secure network slice to actually run the operations in, let's say, the desired manner. And basically, what are the 5G KPIs that should be met with respect to UAV verticals and UAV applications, and basically what are the 5G components that need to be improved to guarantee UAV performance. So to solve that, we have created an architecture that Pascal will describe in further detail, but it encompasses the use base, the 5G network facilities, as well as the trial controller domain that basically governs the entire planning, execution, and post-processing of the trials. We have 8 different objectives. All of them focus on what I've said before. In addition to that, basically, we have been continuously doing an analysis of the performance requirements of UAV vertical applications and business models in 5G. So the way we run the entire project is to first done the requirement analysis of UAV use cases. From that, we have sprung on what are the 5G drones enablers to enable the trials, and also design and development of the 5G drones trial controller. They all meet up at the 5G facility in question. We have 4 of them. So 5 Genesis Athens, Sofia Antipolis 5G Eve, Oulu 5G TN, and Aalto-X network. And then we execute the trials. So that's my part, and I guess we continue to use cases then.
Yes, thank you, Jussi. Ludwig.
Yes, my name is Ludwig Kastner. Welcome from my side, the company Frequentis. Let me share my screen. I hope you see my screen now.
Yes, we can see.
Yeah, Frequentis was industry partner in this project based in Austria, Vienna, and we were responsible for work package 1 among other technical tasks we had in the project. And one of the first deliverables was the use case document. And for this, I would like to give you an overview now. First, I would like to start with a definition of a use case. I think you can find several definitions of this term, but I picked 3 of them. One is a use case is a scenario for usage, suggests situations where the research object may be useful. Then let's define our research project. It's unmanned aircraft systems using cellular connectivity, or following our project name, it's drones using 5G. Another definition of a use case is a list of actions typically defining interactions between a role and a system to achieve a goal. And the third one I picked is a use cases describe the conversation between a system and its users. I think whatever definition you take, there should always be a usefulness of a system for a certain user group. And you will see on the following slides that the targeted user groups are very different for different use cases. The ambition for our use cases was already partly mentioned by Jussi, is not only describing them, but define requirements for the 5G network as well as for the drones, for each and every use case, to define KPIs for each use case, and also trial the use cases. So really implement everything to be able to showcase them. And before we can do that, we had to identify and develop missing components to trial the use cases efficiently. I will come to that later on. And finally, after the use case, to validate the relevant KPIs if they have been met or not, and to what degree they have been met. Example for use case requirements. Requirements to a 5G network could be a certain bandwidth for real-time transmission of HD or even 4K video streams from a drone. It could be a low latency for real-time operation of drones or other parameters. Requirements to a drone could be a high positioning accuracy, a certain payload of the drone to carry sensors or actors, as you will see in some of the use cases, or a minimum speed or minimum flight time of the drone in order to achieve a certain range or cover a certain area with the drone. About the identification of missing components, we found out that to trial use cases efficiently and to achieve consistent and especially reproducible results, it turned out that there is a need to log all activities, for example, the inputs for a use case, and also to have automated monitoring and logging of data to be observed. If you think of 5G network parameters or positioning data, this is a huge amount of data, and is only possible to have an efficient performance of the use case if you log this automatically. Examples for the drones that were used in the use cases. I have here examples for commercially available drones. There were a lot of other drones used which are not commercially available and which will be shown later on in the trial section of today's presentations. But just here 2 examples for commercially available drones like DJI Mavic 2 Enterprise and DJI Matrix drones that were used in our use cases. Then let's continue with the overview of the use cases. We had the first use case group called UAV traffic management with different scenarios, command and control application, then a map and visualization scenario, and a logistics scenario. We have a public safety use case where it's about saving lives, and with the scenarios monitoring a wildfire, disaster recovery, and police and counter UAS scenarios. Then several situation awareness scenarios like infrastructure, inspections, long-range power lines, and even search and recovery in water was considered. And a 4th group of use cases, which is about connectivity during crowded events, for connectivity extension and offloading in such situations. But let's start with the first use case group about UAV traffic management. And the command and control application. What is the goal of this use case? It's to perform command and control of drones using 5G connectivity to manage a high number of flying drones in a shared airspace. So main goal is definitely a collision avoidance of drones. And what are the challenges here? In our project, we definitely wanted to support long-range flights beyond visual line of sight. We want to support automated flights via defined waypoints. And we want to ensure that drones fly at a safe distance. And that a safe distance means from each other and also from other aircraft, like manned aircraft. And finally, we also want in this use case to achieve security and integrity, so protection against the third party taking control of our drones. And let's check what are the required capabilities for this traffic management and the command and control use case. So one of the capabilities you need is the full understanding of the air traffic in the proximity of the drone. To act, you need to have near real-time remote command and control of the drone, be it by machine, by human, or a mixed operation of machine and human. And the command and control could be based on telemetry, which is mainly more suitable for machine control, and real-time video stream, which is in most cases more suitable for human control. So what does this command and control application need in terms of capabilities? If you have a use case with multiple drones flying simultaneously, the application will need to assess a potential risk for collision and enable automatic collision avoidance. So you need a near real-time command and control of the drone, and this requires on the drone side a high positioning accuracy and a reliable low latency communication to exchange control messages. In case a human operator takes over control, you will need a broadband data connection for the video transmission from the drone. So this first use case that I described now was basically, or can be considered as a basis for all following use cases, as the collision avoidance is of course always relevant. But let's continue with the second use case, which was called 3D map and supporting visualization analysis software for UTM. The goal here was to capture 5G service levels in order to facilitate future UAS flights. So it was about populating a 3D map to help drone operators and also flight planners to fly their drones in best possible 5G service conditions. Especially in urban areas, there's a very uneven distribution of 5G service conditions, as you have a lot of shadowing and reflection effects, and it cannot be predicted easily which 5G service quality you will get. So this use case is, as the first one already, is a use case beneficial for all future flights. Because what you will do is to have several flight routes, log 5G network parameters and positioning data. You visualize these parameters in a 3D map, and with this information, future flights can use routes with optimal 5G network conditions. So you will have certain areas which are verified, other areas which are not verified, and some areas that are just optimal from 5G service point of view. Then now let's come to a use case which is focusing on a different user domain. The first ones were focusing on the user domain of drone operation, but now this is a use case focusing on a real end user need. It is about to demonstrate how drones and 5G network capabilities can provide logistic solutions. And the idea is that the sick person can receive a medicine through a personal delivery by subscribing to a drone logistics network, and to use a drone which can carry a medicine to the sick person. And there's a delivery box which ensures communication with the drone logistics network for the parcel drop-off and for the landing. The challenges here in this use case are that the parcel drop-off and landing functions need high accuracy, and between houses in urban areas, a bad GPS signal quality can occur. So what were the considerations we had for that use case is that semi-automated flights with a change to a human control for parcel drop-off is used. So you start with an automated flight and switch then to a human control for the parcel drop-off or landing or both. And the drone streams video over 4G, and the human operator takes over the drone control for the end part of the delivery. So this is the idea for this use case. Somehow, yeah, it works again. And the requirements can be considered alternatively here. Either the drone has a high positioning accuracy, which would be important for automated landing, or you would have to have a high bandwidth in the network for low latency and low latency for human operators video operation. Then let's come to the next group of use cases, which is about public safety and saving lives. And the first one is monitoring a wildfire and disaster recovery use cases. So the idea is that drones can be helpful to localize persons with real-time aerial images and also thermal cameras, infrared cameras. And drones could gather visual and location information on the spread of a wildfire, for example. Then, of course, you need to carry certain sensors for such scenarios, and drones could embed sensors for measuring hazardous substances as well in this scenario. And if you want to cover large areas, then you would need several drones to use simultaneously, and then there would be the need for UTM and swarm control in order to cover a larger area for a wildfire, for example. The requirements for this use case are, again, high bandwidth for the real video transmission, sensor integration, a certain payload of the drone to carry the sensors, and a certain minimum flight time of the drone on the one hand, or a swarm control if you want to distribute the tasks to different drones. The next use case within the group of public safety use cases is a police and counter-UAS use case, where the scenario is that as a part of a VIP visit, a temporary no-fly zone is established, and an intruder drone is detected in the no-fly zone. And the idea is to stop the intruder drone with a police drone. Well, in our project, we don't want to consider counter-UAS measures. This is a research topic which is covered in several other projects and was not part of our use case, but our use cases focuses on finding the pilot of the intruder drone. So the idea is to have a command and control center which has control over a police drone, and with this police drone you take action, and at the same time artificial intelligence notices here a suspicious person with a drone remote controller near a building, and the police drone flies near the suspicious person, instructs the pilot to stop the illegal activity. And our interest here was that a police drone could have privileged rights in a UTM system as long as it is not dangerous to other aircrafts. So this aspect of privileged rights and find measures to achieve priorities for a police drone is the interesting aspect here for our project. Let's come to the third group of use cases, which is about situation awareness. First scenario here is infrastructure inspection. We started with power lines, which have to be regularly inspected for planned maintenance. And the question one could ask here is, why 5G? Why could not 4G already be sufficient to do such an inspection? And our consideration was, yes, it is definitely possible, but under different conditions, because a drone collects large amounts of data which have to be analyzed later. And this analyzation of data is very time consuming, and the quality of the data cannot be verified during the flight with, let's say, 4G technology. And only with 5G, large amount of data can be streamed and analyzed in real time by having the processing power on the edge, on the ground, to have this analysis of high resolution videos and photos, because an onboard computer for analysis would be too heavy to be carried. So we think that 5G definitely adds enormous capabilities for such a use case, because you could change the flight plan immediately, for example, and investigate areas with potential problems directly during the flight, in contrast to a scenario with a post-processing of the data only. And we think that 5G drones inspection lays the foundation for fully automated systems in the future. If you think of drone-to-drone communication, this opens door for even much more enhanced capabilities. Then next use case about situation awareness is inspection and search and recovery operations in a large body of water. So you doing water survey operations using a hybrid air and water drone. And this was one of the special type of drones we used in our project. This hybrid drone is equipped with required sensors like water quality probe sensors, sonar leader sensors, or even water depth sensors, and can patrol on the water and gather data. And like in the previous use case with the power line inspection, this data is then processed in real time to produce a report like on water quality or underwater depth. And without the 5G, the lack of embedded processing power would just put a limit to this scenario. The drone would fly in a semi-autonomous mission with a part of automated flight and the landing with the human control. And the interesting thing on this special type of drone was that the hybrid air and water drone has rotating propellers. You can see them on the picture. They are in vertical position, so they can move from horizontal to vertical position to move on the water surface. And the sensors of the drone, yeah, could be of any type like water quality or depth sensor. Yeah, then let's come to the last group of use cases, connectivity during crowded events and connectivity extension for crowded events. So what was the idea here? The idea is that high user densities during events can lead to higher connectivity requirements in certain areas where you usually don't have these high user densities. And the question we ask ourselves is, how could a drone improve connectivity services in such a crowded environment? And all starts, of course, with the initial measurement of the radio network quality to have a baseline and consider which parameters of the network you can improve. And basically, we found at least three variants for how a drone could be helpful in this scenario. First would be that the drone carries a 5G base station, which would probably need a cable for the backhaul connection to the 5G network, core network. And having a cable to the drone would then also give the benefit of having the chance to do the power supply via the cable and have unlimited flight times by doing the power supply via these cables. A second option would be to have the drone as a relay function or repeat the function of to the 5G network. And with this relay link to improve coverage. So you would reach further and increase the coverage of the 5G network, but not the capacity, in contrast to the first case. And the third variant of this use case was that the drone acts as a Wi-Fi hotspot with a 5G backhaul connection. And you could offer local content for such an event, or you could offer free Wi-Fi services for this event. So this basically was the last use case of the presentation. And is basically the content of our deliverable one in work package one, which was the baseline, basically the start of the project for all following activities.
Salve.
Yeah.
Salve.
Thank you very much. Are there any questions to the use cases?
Somebody have a... some background sound music. Yeah, thank you, Ludwig. next we're gonna have a network presentations of all, and this will be the short 5 minutes presentation, and we will start with Harilaos.
Yes, thank you, Vero. Let me share my screen. You can see my screen, I guess.
Yes, we can.
Okay. So, hello to all. I am Dr. Harilaos Koumaras from NCSR Demokritos. And following the presentation of the use cases, I'm going to summarize very briefly the Athens platform, the 5Genesis Athens platform that was used in order to support the presented use cases, and especially the last category for connectivity extension. The realization of this use case on top of the Athens platform was performed with close collaboration with the specific numbers of partners that listed in my presentation. So this is a collaborative work, and it's not only NCSR Demokritos work. Just to mention that the Athens platforms is actually originated from the 5Genesis platform. It is a 5Genesis is one of the ICT 17 projects that were funded in order to develop 5G experimentation platforms across Europe. The specific platform in Athens is composed of 3 different sites and domains. We have one main domain in the Demokritos campus in Agia Paraskevi in Attica. And then we have 2 remote sites, one in Cosmote campus and also one in Hellaoui city, and specifically in the football stadium, where also the final showcasing event of the project took place. Now, a few words about the platform itself. The Athens platform is not only composed by pure 5G infrastructure, but is also equipped with some experimentation capabilities that were also used in the framework of the 5G drones project, and which also homogenized in order to be able to report the measured data and the captured measurements in the same way, using the same visualization reporting tools as the rest of the 5G drones project. This helped a lot in the comparison of the results. And specifically for Athens, we offer an experimentation portal where the experimenter can go and set up the 5G experiment. Then we have an experiment lifecycle manager, which together with the automated experimentation tool, the OpenTap, performs in an automatic way the reception of the measurement during different repetition of the experiments. And then we have a layer which is related to slicing, to slice manager, and the orchestration of the virtualized resources, both at the core cloud or the edge cloud across the network. Now, in terms of 5G components, the platform includes 2 different deployments. We have one deployment that is more portable, that actually used during the final showcasing trials in the stadium of Hellaoui city for specific experiments that have been designed for this portal demonstrator. But we have also a real commercial van, 5G van, that was provided by Cosmote partner, the Greek mobile operator. Again, this setup was performed in the Hellaoui Stadium in order to assist the execution of some use cases in a more commercial grade 5G network. And now, concerning the demos and the use cases that were delivered during the Athens showcasing event, the last trials, was a drone autonomous flight, first of all, over 5G, the C2 delivered over 5G. And then we have the coverage extension, which was performed with Wi-Fi extension connectivity. As you can see, the drone was equipped with this 5G CPE. So the 5G connectivity was used as a backhaul to the 5G network, and this CPE created a Wi-Fi host over a specific area of the stadium, where the audience was able to connect with Wi-Fi 6 and offer to them high-speed connectivity and free Wi-Fi speed, as also previously described. The Athens platform also hosted a great variety of different drones that were used for the execution of the use cases across all the duration of the projects. As you can see here, we have different types of drones allowing us to assess the 5G integration to the drone industry using drones of different specifications. And also to mention that some of these trials were not only performed in the stadium of Hellaoui city, but also in Cosmote OTE Academy campus as well, and also Demokritos campus, where actually were some pre-trials before the final execution of the showcasing event in Hellaoui stadium. That's all from the Athens testbed. I give the floor back to Tero.
Thank you, thank you. Next, there will be a Karim, 5G Eve network.
Good afternoon. Let me share my screen. So I'm Karim Boutiba, a PhD student from Eurecom. Today I will introduce Eurecom 5G facility, which is a 5G platform that allows vertical users to define, trial, and test vertical use cases on 5G network. In the following slide, you can see the Eurecom premises in Sophia Antipolis in the southeast of France. In Eurecom, we have two types of deployments, standalone deployments and non-standalone deployment. Everything is based on open air interface platform for both radio part and core part, except for radio units. For radio units, it depends on the mode of the deployment. We have outdoor deployments, as you can see in the picture. We have two antennas outdoor, and we have indoor deployments. For the outdoor deployments, the radio unit is based on AW2S split 8, using band 38. While for the indoor deployments, we have several scenarios using both USRPs, AW2S, Mavnir Open RAN 7.2 radio unit. And soon we will support millimeter waves on band 258. Eurecom facility will allow the use case owners to have different services like URLC. We are achieving less than 4 milliseconds round trip, and MMTC using LTM. And for EMBB services, the peak throughput we are reaching is 800 megabits for downlink and 660 megabits for uplink. This is using a band of 100 megahertz indoor. And for the cluster we use the cluster based on OpenShift on Dell servers. So everything is running as a microservice on this cluster. In Eurecom facility, we have three different planes: the vertical plane, the management plane, and the infrastructure plane. For the vertical plane, we propose a web portal, which is a graphical web interface that allows the trial owner to define the different parameters of its trial, like the applications in use in format of cloud native applications. So he needs to define where is the image. Is it locally in the facility or in Docker Hub, or it's in a private GitLab? Then he defines the networking parameters like the IP addresses, if this interface is exposed to internet or locally in the facility, and some environment variable needed in his applications. Then using this web portal, he will create an NST network slice template and pass to a slice orchestrator. The slice orchestrator is the main components in the management plane. It will divide and manage the life cycle of the slice between the different components of the facility. So we have the NFVU responsible on the cloud domain, and we have the RIC responsible, the RAN intelligent controller responsible on the RAN domain. So the NFVU will take the description of the application and deploy it on the top of the OpenShift cluster, while the RIC will take the slice description and deploy it at the RAN sites. I recall that everything on the infrastructure is composed of OpenRAN interface and the OpenShift cluster. Besides, Eurecom provide a map platform composed mainly of the RNES service and the traffic redirection services. So all the application deployed on the cluster can use this standardized map services using the MP1 interface. And for the MP2 interface, since it's not standardized, we propose to use X apps to provide a standardized way to have to interconnect the map platform with the RAN site. And for the core network side, we will use the NEF to standardize the exposure of different network functions to the map services. So for perspectives of our facility, it will be the use of the web portal for more on-demand networking oriented. For example, some customized 5G core network functions or more customized CUDU components in the context of ORAN. Besides, we will use P4 switches as UPF to increase the throughput at the transport network. This is all from my side. Thank you.
Thank you, Karim. Okay, yes. So next, it will be Jussi. Jussi, you are muted.
Yes, sorry for that. Okay, so I'm presenting the 5G test network, which is a part of the University of Oulu 6G flagship. So within the context of 5G drones, presenting the following. So our 5G TN is not entirely new concept. So even though it's not an ICT 17 facility, we have the first, we started running the 5G test network back in 2015. And it's an evolving system with a clear pathway to at least 4 years forward, and it will slowly evolve from firstly from 4G to 5G to 5G plus, then to 6G components. So we are running 3 different, let's say, prongs towards 6G path. So we're following the 3GPP path. We are following the ORAN path, and then we're, as a research institute, we're also considering a disruptive path, how to reach that goal. So during the 5G drones, our network, essentially we have a standalone as 5G on N78 band, and we have also a non-standalone band. So we have 2 macro stations, and we have several indoor non-standalone 5G base stations distributed throughout the University of Oulu campus. Also, we have a 4G coverage, which is covering a significantly higher or a larger area, and essentially the entirety of this map, even a bit further In addition to that, we are running several hundreds of sensors around the campus, monitoring constantly different parameters of the campus area, especially related to the well-being of the building and the people over there. So that can be visited at Smart Campus website. In addition, we have a lot of different applications that are somehow hooked or investigated within, like energy consumption of researching a fully renewable energy run 5G, etc., etc. So our baseline architecture is that we have there everything is within, of course, isolated but a unified network, so we can connect components within the facility as desired or needed. So we have a production grade non-standalone VPC connected to a macro station and the indoor stations. Then we have an open 5GS standalone core connected to a macro station outside. We have a USRP running open air interface and in addition to that, we have hundreds of LoRa sensors, and we are connecting all kinds of different equipment. So we have constantly running, of course, serving the entire university with different application areas, but also we have partners coming to test out their equipment or their services within our network constantly. With regards to 5G TN within 5G drones, we have been so early phase in the project. We ran the non-standalone production grade 5G network for testing and verification purpose, and then we transitioned to open 5G based standalone. It's compatible with release 16. We are using Kubernetes and Docker containers for edge processing and installing edge applications. We have the project web portal 1.2 abstraction layer and 5G TN facility adapter available at the University of Oulu, of course. For the trials, we were using the Aalto web portal 1, etc. And we have open source Mono microstack as a version of OpenStack that we're running. In addition to that, we have a fleet of drones, different kinds of drones. We have user equipment, so mobile phones for supporting standalone from several different vendors. In addition, we have modems, Quectel modems, and some others which we can connect to the network. Shortly about the 6G flagship. We are running 4 different strategic research areas. Basically, all of them exploit this 5G test network evolving towards 6G network. So we have 4 different strategic areas, which is researching wireless connectivity solutions, devices and circuit technologies, distributed intelligence and wireless computing, and then sustainable human-centric services and applications. And thank you.
Thank you, Jussi. So next it will be Hamid and Aalto University.
Yeah. Thank you, Tero. I'm sharing my screen. I guess you can see it.
Yes, we can.
Perfect, perfect. So my name is Hamid Hellaoui. I'm from Aalto University, and we are a partner providing one of the 4 facilities used for the trials of some use cases of the project 5G drones. So basically, X network, our facility is not on ICT 17, which is actually based on 5G TNF from Business of Finland, 5G test network Finland. So the trial site is actually connected to different to other trial sites, including Tampere and Oulu, and the trial site is managed by or in collaboration with Aalto University, VTT, and Nokia. So our trial site is located in Aalto University Otaniemi campus, and we include, or the trial site includes different components at different level. For the radio access network, we do employ a number of E-Node Bs and G-Node Bs, including Nokia AirScale G-Node B and Nokia LTEs, and also narrowband IoT LTEs. We do also employ at the core level a number of EPCs and 5G core networks. For the edge servers, it's actually used to accommodate vertical applications and to orchestrate them. So in addition to a Nokia Mac, we do employ a local or a home-made edge server. And for the user equipment, we have been working with a number of user equipment to provide connectivity and to connect them to our network. So that was the overall view of our facility and for what we've been using in the context of 5G drones. So for the user equipment, we've been mainly relying on some phones, more precisely on Nokia X20 and Nokia XR20s, and also some coaxial modems in order to provide connectivity to the flying drones, but also to the laptops, which are used to control the drones and access the network. For the G-Node B, we've been relying on Nokia AirScale G-Node B, operating on 3.5 gigahertz. For the 5G for the 5G core network, we've been using Como core network, which relies on release 16. And for the edge server, which is, as I mentioned earlier, it's actually used to accommodate vertical applications, the applications that are used to control the drones. And we have been using our home-made edge server in a way to orchestrate these applications. Since the project is about evaluation of KPIs, there have been an effort to let's say implement and to evaluate, to capture some KPIs. And in Aalto University or in our trial site, we've been collecting KPIs at 2 levels. The first one is at the UE level, where we have some scripts running on the phones in order to collect some network KPIs, but also some uplink and downlink speeds and latencies. And the second level is related to the edge server, where we accommodate vertical applications in a way to monitor the consumption of resources in terms of CPU, RAM, and data transmit and the data being transmitted and received. All those KPIs are being collected and sent in real time to the upper layers of the project. Yeah, this slide shows the location of the trial. So basically, this is the Otaniami campus, and this is the G-Node B, which is located on the top of Very building. So we've been running trials on, let's say, in the parking of the TOAS building. And the reason is there are a lot of constructions around the campus, and this is the place where we have been flying drones and trialing the use cases, which is around 300 to 400 meters from the G-Node B. So this is actually my last slide related to the trial site of Aalto University.
Thank you, Hamid. So next we will go a little bit more deeper about our architecture, what we were using. So Pascal. Pascal, you are muted.
Hello, can you hear me now?
Yes, loud and clear.
Can you see my slides as well?
Nope, not slides yet.
Okay. Okay, let me check. Sorry about that.
Yep, now we can see.
Okay, very good. Apologize for the small delay. Okay, so I will go. So good afternoon, everyone. My name is Pascal Bisson. I work for Thales, so 6 GTS France. I will make this presentation on behalf of my colleague Farid Benbadis, who is the technical manager of 5G drones. I'm the technical manager deputy, and I did prepare this slide together with Ludwig Kastner from Frequentis. Just to introduce you to the 5G drone system conceptual representation. So this was in scope. This architectural design was in scope of Objective 2, which was already part of the objective introduced by Jussi. And the objective was to design and implement the 5G drone software layer or system, as we call it, to execute the UAV trials. So the 5G drone system can be conceptually described by 3 actors we have identified. So the UAV verticals, top, the 5G trial controllers, 5G drone trial controller, and the 5G facilities, which were already introduced to each of you. And so we have 4 considered, 2 coming from ICT 17 projects and 2 others coming from other organizations. Between this 5G infrastructure, 5G facility and 5G drone trial controller, we did manage to come up with an abstraction layer in order to ease the communication between the two. And we also had to develop a northbound API to collect trials to be conducted by the UAV verticals. So this was the starting point for our design. And coming to the initial 5G drone architectural blueprint, as depicted in this picture, you see the internal components we had identified. So the portal, the trial controller, the abstraction layer, the 5G facility, infrastructure monitoring, the use space entity, and the use space adapter. This high-level conceptual architecture reflects 3 distinct actors, as already introduced. So the UAV verticals, the 5G trial controller, and the 5G facility, whose interaction reflects the overall approach taken by the project regarding how the selected UAV use cases will be trialed over these 5G facilities. Going to the next slide. So this shows you some view of this 5G trial controller, which was made of web portals and trial engine. And you see also the interaction with the facilities and the network slicing concept and the UAV functions in order to collect data and get back to the KPI monitoring we had to perform, but also a connection between the trial engine and the trial enforcement in order to make happen the trials. So this is more or less how it flows. And the next slide is this.
Excuse
Yes.
me, it's a little bit problem. At least I can't see, like I'm still seeing the first slide on the presentation, so maybe.
Ah, okay.
Yeah.
I see. Because I see them on my slide.
I see that you're now in the slide 3.
I am on the slide 5 indeed.
Okay, I see slide 3.
Okay, so it was. Do you see them now?
The first
Now
slide,
I see.
the title
Yeah,
one. Maybe you can try to share the whole screen or something, which works better. So.
Yes, maybe you can present the slides on my side, Jussi, because I have an issue there. I apologize for this.
Okay, we'll do that.
I am on slide 5.
So just wait a small amount of time. Okay, I will share. And slide 5. Slide 5.
Yes, that one.
Yes,
Yes.
that one. Yes.
So thanks.
Thanks.
So following the work done on initial architecture, we did work on investigating and detailing the specific requirements and capabilities for each of the components. And this led us to the final 5G drone architecture you can see here, which reflect the 3 distinct conceptual domains we achieved, which are the trial controller, the use space, and the 5G facilities. This high-level architecture view indicates that the experimenters initially interact with via the web portal with the trial controller domain to describe the scenario, along with the technical description of the network slices and the target KPIs to be evaluated. The trial controller domain coordinates with the infrastructure controller domain, so has to run the different experiments on top of the 5G facilities. Furthermore, in order to validate the trial and ensure safe access to the airspace by the drones, the trial controller domain also interact with the use space domain through a dedicated interface. Next slide, please. So the 5G drone final architecture addresses 3 domains. I will not remind them, you see them. And we added some refinements with respect to the web portal, which was divided into the following part. So the web portal 1 define the drone flight plan, select the 5G facilities, as well as obtain the flight permission if necessary, and 5G coverage verification. The web portal 2 is important for definition, configuration, verification, and triggering the experiment in regards to 5G and make setup aspects. And we also have this dashboard for monitoring the status of the running experiment, including the KPI and UAV resource usage, network and UAV resource usage. Next slide, please. So the Trial Engine is a module responsible for translating the description of the scenario to an execution script involving the full UAV and network service components to run over the 5G facilities. And it is made of the trial translators that maps the trial requirements enters in the web portal by the UAV vertical to the required components in terms of 5G facilities and UAVs, and the trial validators that reflects the module for dispatching the validation request to other internal or external module, as well as collecting and presenting the answer to this request. So the trial enforcement design the modules that effectively run the trials as per the request of the trial execution engine. And it includes requests for deployment as well as requests for runtime, configuration, and update. Next slide. So we also have defined in the context of this architecture a number of repositories within the framework of the trial engine with the aim to organize data storage that is important for the experiment. And these repositories includes 5G facility repository, the VNF repository, the UAV repository, and the predefined trial repository. So the VNF repository also different VNF required to run UAV scenario on top of 5G trial sites. The UAV repository holds information about hardware available for use case, including available sensors and availability in time, location, as well as flight characteristic. And the trial repository acts as a centerpiece for the trial controller storage and shall include attributes referencing both UAV and 5G facilities. Next slide. So for the internal architecture of the abstraction layer, it has been composed of 3 components. The first component is the service lookup repository that all details about how to reach the trial facilities and the parcel services. The second component is a router which is responsible for forwarding the generic requests sent by the trial controller to the targeted facilities after translating them to specific requests using the parser services. And the last component is set of facility-specific parser, which are responsible for translating generic requests to facility specific for translating generic requests to facility specific requests. Next slide. So in the meantime, we investigated some open source tools that can be used for the abstraction layer, and the consortium has identified a solution which would be used for the router and service lookup parts, and which is called Kong, and that comes with integrated security and KPI monitoring features, which was added for the project. Next slide. So the key takeaways are for this 5G drone architecture. It has been released through a couple of deliverables. So the first is initial design, and the final design has been released, and you have the link to this slide. It was designed to serve the project purpose, at least to meet the requirements coming from the use case, and also to further extend 5G platforms in order to support or be appropriate for drones use cases and drones application. This for 5G to reach its full potential with respect to this vertical. So it has been released, and it has been also widely shared with targeted and interested communities of stakeholders, not only 5G and drones, but also some others. This is also good material for 5G and beyond and 6G. It also provides, as per the design, a neutrality to the platform, as you have seen, and we support, and this has been, the design has been used to extend the platforms which were represented within this consortium, and obviously it can also be used for other platforms. And it shows also an efficient integration of the US ecosystem with 5G services by providing detailed information of about the UTM, UAV operator, and UAV, and also how it could be done. Right? It could be further developed, as we will see in some of the next presentation. That's all from my side.
Great. Thank you, Pascal. Well, we continue. We are luckily on schedule. So we continue with Tanel about 5G drone trials what we had. So go ahead, Tanel.
Yes, good afternoon all. Hope you can hear me, you can see, and I will start sharing my presentation. Okay, just
remember, Tanel, to click that slider that you get the audio.
Yes, yes, I believe we can manage it. Yeah. I will start sharing again. Screen. Presentation mode. And hope you can. Hope you can see my screen. It's a presentation in PowerPoint. Good afternoon all. My name is Tanel Järvet from CAFA Task 4.2 trials lead, and a short overview of 5G drones trials. First of all, we conducted the final trials this year in 2022 in Finland, Greece, and France. In Finland, as mentioned previously, in Helsinki at Aalto University, at Oulu University platform in Athens, and also at the Eurecom Institute platform. You can see different dates, very intensive August and September period. Why we used this test and trials? Because our project used an iterative process. That's why we planned and we conducted three iterations. First one, feasibility test in 2022. Then technical test, first and second round, 2021 and first half of this year. And final trials, 2022. And our motto is practice is a criterion of truth. And as we are developed and tested very complex technologies, then we used this on-site test. During the COVID, yes, we conducted some remote tests also, but just after the COVID, we started this on-site test. All partners participated, some partners remotely, but we acted as a single 5G drones team. The next slide is the video describing trials at Aalto University. I will explain a little bit the content also. You can see Aalto and CAFA tech team preparing trials. And the architecture described here, we conducted, first scenario was the logistic scenario, conducted by CAFA tech, and it was fully automated logistic flight over 5G standalone network. And we used video streaming for the teleoperation, as Ludwig Kastner previously mentioned. The teleoperation over 5G is very useful. And as you can see on the right side, that our drones were connected to the Frequentis and drone radar UTM systems. So our drones were visible for other air traffic stakeholders, manned and unmanned aviation operators. Let's continue. You can see Aalto University Web Portal 2, which we used for planning and slice creation and measuring KPIs. CAFA delivery drone, we deliver at paracetamol, small packet. And logistic flight controlled over the C2. You can see the C2 software, how the drone flight actually conducted, and all these technical parameters also. You can see our drone and plane. It was the main idea behind the UTM system. I will stop the video here. You can see the Frequentis UTM system. You can see the CAFA drone visible for other manned and unmanned air traffic participants. And we can use this UTM system to check the other manned aircrafts also. Let's continue here. We used a parking lot behind the Aalto University building, and mission completed successfully. As you can see, the paracetamol delivered. Aalto University team conducted IoT data collection drone flight. Also used trial controller vertical services. And you can see how Aalto team prepared for trials, a lot of developments, and the drone. The takeoff. And drone flight at altitude, it was 15 meters above ground level. You can see the C2 system used by Aalto team. And KPIs. Key panel results, screen recordings. We recorded all our trials in project and all project partners. So here. Next slide, next video, describing Oulu University videos and trials. As Jussi mentioned, yes. We used 5G test network you can see the botanical garden, and now you can see the parking lot. Two main areas where we conducted our 5G drones trials. First mission, Nokia and the University of Oulu mission to measure the location data. You can see drone carrying the Nokia measurement device. A lot of technical discussions, some screen recordings here. And next mission, preparations. CAFA conducted 3D mapping flight. You can see the parking lot here. The 3D analyzer describing the quality of service measurements. And the next mission, fully automated police drone flight controlled over 5G standalone network. We used video analyzer application and drone as a surveillance platform. It was fully automated flight. Police created restricted area, and police created also parameters to detect blue hat, person wearing the blue hat, and drone conducted its automated mission. And you can see one of our partner carrying blue hat and how the drone flying, computer vision analyzing the video feed, and as you can see, the blue hat detected and drone landed after a successful mission. Also, we used UTM scenario. And next one is the Flaperon and Hepta airborne power line inspection scenario using the LiDAR and cameras. And they conducted this mission in botanical garden area, ground test in parking lot. Very powerful heavy lifter drone. You can see it's a mock-up power line also here. And the LiDAR mapping results. Quite huge propellers. And now the next scenario conducted by Alerian team from France, the search and rescue mission using Alerian hydrodrone with bathymetric devices. The technical test of the parking area, and now you can see on the lake Alerian search and rescue drone conducting the mission. And after mission, they created this measurements visualization also. University of Oulu conducted cable drone scenario. They used a LiDAR and 5G phone. You can see the cable drone working, carrying the LiDARs. And after these scenarios, we also tested 5G drones Web Portal 1 and Web Portal 2, different functions to supporting our drone partners to use the 5G network. You can see the UTM screen here, and you can see now the slice creation procedure in 5G drone. And 5G drones local showcasing event also happened in Oulu University. We answered the questions and we showed the different scenarios. You can see the Nokia and University of Oulu scenario, and handshaking just after successful week. It was almost the 7 days final trials, field trials in Oulu. Next slide, next video describing the trials in Athens. You can see a lot of technical discussions, preparation with Demokritos team. First, we conducted 3D mapping flight. We collected a lot of photos and created a 3D map for next 5G quality of service measurements mission. You can see CAFA 5G cellular drone with Quectel modem on board it and prepared to conduct, you can see the drone, and to prepare to conduct 5G quality of service measurements. The drone mission and the actual flight on the municipality of Hellaoui Stadium. Drone measured this 5G quality of service parameters, and you can see the custom application showing the different measurements and CAFA 3D analyzer measurements results. The next mission by the Demokritos, Cosmoti and Anandlife and HEPTA and Flatperon team. I will stop here the figure. You can see 5G booster van from Cosmoti, the commercial network. You can see that our drones were visible in Frequentis and drone radar UTM system. And we used unmanned live and HEPTA and Flatperon technologies to conduct this connectivity extension and offloading scenario. I will continue here. And you can see quite big drone carrying the connectivity extension device. Some emotions just after trials. And yes, first week of September, very fruitful, intensive, but successful week. And last trials at Eurecom, 16th and 17th of September this year. Eurecom, Involi, CAFA teams, we conducted the on-site trials, a lot of technical preparations also. I will stop when the figure, architecture figure is visible. And then, yes, you can see. We tested UAV integrated to U-Space. CAFA conducted automated drone flight, and our drone carried the Involi Lehman tracker, and this tracker shared the drone location to the Involi receiver system, forwarded to the signal and data forwarded to Involi central server. And the Involi central server is connected again to the Frequentis and drone radar UTM systems to show our drones real-time location to other unmanned traffic or manned traffic aviation stakeholders. And we used Eurecom 5G base station standalone network, and we installed and used Docker container deployed an Eurecom OpenShift server. Let's continue here. And you can see again the technical, a lot of technical preparations, and Involi receiver here, and the actual drone flight just behind the Eurecom buildings. And it was automated drone flight, drone carried, Involi tracker. You can see different screenshot, and again, you can see the, I will stop here, and you can see the Involi. Let me share this one. You can see the Frequentis and drone radar UTM systems showing the drone real-time location. You can see our 5G drones project web portal, also the created area for drone flights, and Involi system showing different real manned aircraft at the same time. We used web portal 2 and created slice. And you can see the Eurecom portal currently working. The second scenario conducted at Eurecom platform in France was mission critical service scenario, and that drone and the 5G phones video streams streamed for Airbus mission critical service. The mission critical service container deployed at Eurecom, and this scenario was also successful. As you see, there are a lot of emotions. Then I will share the links. Our 5G drone trial videos are available on YouTube. You can check it on our 5gdrones.eu website. And, again, we started technical test Oulu 2021, and some comparison between 2021, 2022, Oulu, Athens, some group photos, Eurecom, and that's all from my side. Thank you very much, colleagues. Thank you very much, partners. We acted as united team, great team. Thank you very much.
Thank you, Tanel. Just on time. Okay, we're gonna have a last session before question and answers, and Pascal. Pascal, you
see?
might be yes.
I have just unmuted. Can you see my slide now?
Yes, we can.
Okay, very good. Okay.
Sorry, just to interrupt. If the screen doesn't transition in the your lower left-hand corner, you can see the slides, and if you click forward, you have a chance to sync with the presenter. So please do that.
Okay. Let me check. Yes. Okay. Okay, so this final session is devoted to key main takeaways and also lessons learned. I will start with this first lessons we learned, meaning that this 5G drone project was a flagship project funded by the EU, but also under the umbrella of 5G PPP work program, which was also key for us to cross-fertilize with others. And this project was fully devoted to 5G enhancements to support UAV verticals, as it has mobilized 20 partners who have been working very hard and delivered a lot of useful and usable results. This is what we have tried to achieve and what we achieved towards both 5G drones, UAV communities, and even beyond. So this is also something we wanted to stress, that the fact that these results were shared and they want to be used and continued by others, and also of value for a number of communities. The second takeaway or lessons learned, that even if we could argue that a number of things could already been done using 4G, the 5G drone project did manage to demonstrate quite successfully, as it has been shown, that we could go far beyond thanks to the enhancement and the new capabilities which were brought by 5G, but also by the project itself, as you have seen. Overall, for us, it opens new alleys towards both effective and efficient drones application through what has been delivered and also trialed, demonstrated. The fourth takeaway is related to the fact that we see this project also as an opportunity for all to learn from each other, this was especially true, and this is what we did for especially learned for mobile operators who have learned and have managed to get a better grasp on UAV operators' constraints and aerial regulation in order to better support through new 5G network function, introduce, also improve and assure aerial connectivity by performing 3D coverage measurement. This led us to findings which can be used in the spectrum of standardization work, but also in the regulation for the spectrum itself. The fifth takeaway would say that end-to-end slicing mechanisms for drone control and payload transmission was at the heart of the project, since clearly differentiate 5G from its predecessors. Nevertheless, when it comes to the test, we did realize that existing mobiles are capable to serve only one slice, which was a limitation, whereas there is clearly a need, and there was a need to work with at least two slices, one for control, URLC, and the second for payload, EMBB. As such, we highly recommend to have this addressed in the near future, and this is something in which we have also a number of action items and opportunities for future calls. So the next takeaway relates to the fact that the project did manage to demonstrate highly innovative concept, as it has been illustrated by the proof of concept for Follow Me Edge solution, which was developed by University.
Sorry, this was Aalto University, not Oulu.
By Aalto University. Which moves the UAV pilot software following the mobility of the UAV across a bigger area, multiple G0B, as it has been presented. So this is a concept which is also important, as it allows to reduce the latency of the signal exchange between drone and UAV pilot software at any location. And this live migration happens when the drone is crossing the area covered by one edge server and enters another one. So service is developed, is working without interruption and the latency is maintained low despite of the mobility of the UAV, as it has been demonstrated. The next takeaway relates to the fact that the project has been also an opportunity for UAV industry participants learn about the new opportunities brought by 5G. The idea was that the UTM communities, drone manufacturers, and drone service provider could learn from each other. So I have an issue with this slide. So the next takeaway is the fact that the work we did on the architecture, ranging from an initial architecture to a more complex one up to the final architecture, was really helpful, and it helped to end up with progressively with a very comprehensive architecture and very useful and manageable and implementable. And the level of complexity which was progressively introduced was able to be managed, and this is also what we have learned, and it's always good to have to get things simpler right from the start to add some complexity afterwards, and this was one of the lessons we have learned here. Probably the last takeaway, that the fact that the project, and especially the academic institution, have been working a lot, and this has created a number of papers. This led opportunity to have papers which were published to journals and acknowledging 5G drones. And this was also important for us to present our work in the context of many conferences and workshops. and in order to disseminate the work broadly. And we must also say that 2 thesis publications in University of Oulu were done in the frame of the project, and we will also to pinpoint the fact that all these publications toward the community have been made available and are available on the project website. I think this ends my presentation, so I think we could now go for questions. I leave the floor to you. Sure.
Thank you. Jussi, seems like you have
yeah, so I could actually
nasty echo.
I could give a sneak peek on deliverable 4.4 key takeaways that will be described soon, unless we want to go directly to questions and answers.
We still have some time, so please ahead.
Okay, so what I'm going to present next is a part of our deliverable 4.4, which is going to be published on our website next week, late next week. It's the, let's say, final publication on trials evaluations. And I invite that all of the project partners who are here, like when I'm addressing the scenario, if you have something that you want to point out, then please do so. Having said that, I will share my screen. Okay, so deliverable 4 key takeaways. So first we go to the UAV traffic management UTM command and control application. So the use case 1 scenario 1. So as said before, the use case 1 scenario 1, so the UTM is were completed by a number of flights because they essentially belong to all UAV operations. So, but specifically for this category, there was a receiver feeding airplane traffic to Involi server, where basically it was fed into a Frequentis UTM system. There was a remote ID tracker as well. And we could conclude that the streams were stable and well above the minimum refresh frequency requirements. So the test demonstrated the capability of deployed components to provide the live data to a UAS operator. So basically increases situational awareness. The same data stream can be fed into air traffic management, so manned one, so assuring that there will be a possibility for coexistence and collision avoidance. So just to show out of the map, so here this was done in Eurecom facilities, this particular scenario, and you can see on the map there are the real planes and the drone flying UAV at the same time with distances, etc. So on the right-hand side, you can see the latency of the C2 application, and basically with a 90% confidence, the sample size or with 1 kilobyte sample sizes, the latency is below 12 milliseconds. So in other places, okay, the use case 1 scenario 1 test showed that basically using a cloud native containers for C2 and UTM integration plugging is a reliable and effective solution. So the CAFA conducted fully automated drone flights using a C2 container. The 5G standalone communication was uninterrupted, basically, which is very important for operations. Generating a 5G standalone slice using the web portal 2 is an important value for drone operators because you don't have to be extremely aware of how technically do it. You can just request it, specifying what are the criteria that you need for your operation, and then you can request a slice to be created. Okay, of course, naturally, when the drone is on air, so maintaining communication is mission critical, and basically there needs to be always the connectivity with the drone. So the OpenShift server enabled, the deployment time is less than 15 minutes, which meets the expectations of the drone industry. If we jump to use case 1, scenario 2, which is 3D mapping and supporting visualization. So this is the cable drone. We found out that the cable drone, well, I mean, it serves well its purpose as a replacement. So you can really investigate difficult scenarios before you actually committing to a drone flight. So you can have very high payloads in excess of 20 kilos. There is, I mean, the permission procedure is fairly straightforward because you're not actually flying, and it can be also operated automatically without a pilot. So it's a very good tool for that to actually, before like testing new equipment, new algorithms, so forth out before actually committing to real drone flights. With regards to UAV logistics, so the test showed that the native containers for C2 and UTM integration plugin is a reliable solution. So since drone logistics, they take place in cities where the use of drones with cellular connection is extremely important. Basically, it's really important to ensure the communication and be able to take control over the teleoperation mode. So you need both good video, image, and low latency. These are the factors that 5G can quite reliably provide. Also in Aalto, the Docker containers were basically enabled within less than 15 minutes, which is required or desired. With drone logistics, so we used COSIM scope as getting data from the network itself, and the CAFA C2 containerized system picture is here, which also Tanel showed in the video. With regards to public safety and saving lives, so the results obtained in this use case are encouraging, but there's still things to be done. So it needs to be taken out under real conditions and tested. It also needs to be tested with a significantly higher amount of drones to actually have an effective implementation. So there are a lot of lessons learned, and then this is something that can be developed further. The KPIs that we obtain, they're quite compliant with basically the use case requirements, but further testing is needed to actually verify them. So regarding service creation, so it's the 5G enables something really new as compared to 4G, because you can actually create services like within a very low amount of interval. For example, let's say less than 15 minutes, which is quite critical. So public safety, saving lives. So wildfire scenario. So the slice creation time diagram here. So it's actually creating a slice at the Eurecom facility is typically, or average is out with less than 2 minutes, which is very good. And also on the right-hand side, if you can see, there is a comparison of latency between 4G and 5G, 4G being red, 5G being blue, and you can see that the 5G latency cable is typically only ordered just over 10 milliseconds, so 11, something like that, whereas the 4G latency has a significantly higher amount of variation. So regarding the police scenario, So these tests were done in Oulu. They showed that basically 5G drones architecture and practical implementation can fill the UAV operator and 5G MNO's requirements, performing safe and little time-consuming 5G controlled UAV flight planning and execution. The prototype was fully functional and it successfully carried out the mission. Majority of the now within this context, since we have like a federated trial controller, we have a lot of modules distributed around Europe. So majority of them were in Aalto University in Espoo. The trial validator and KPI control, so KPI component monitoring are hosted at Frequentis in Austria, and the facility web portal and the facility adapter in Oulu. So I mean, making the interplay using VPNs and everything is not extremely simple. So a lot of streamlining needs to be done in order to actually make this a more automated process. So with regards to public safety saving lives, you saw the video and you saw the visualizer and the AI software being able to identify the culprit in an autonomous flight. So the 5G TN baseline KPI measurements with regards to latency and jitter is that the latency is for one direction, for downlink is somewhere around a bit less than 7 milliseconds average latency. Uplink is slightly over 10 milliseconds, and jitter is well confined within a couple of milliseconds for downlink and the average of 5 milliseconds jitter for uplink. With regards to situational awareness and 5G QoS measurements, so monitoring the performance over large-scale commercial network gives good insight on the overall availability and resiliency. So the results of this use case, they highlight the capabilities of current commercial 5G networks for supporting constraints defined by UAV partners. Typically, the measured latency is much higher than the value defined in the project. And the throughput varies with the distance of the UAV and the associated base station, so the constraint can be achieved when the distance is about several kilometers. So, and when you have handovers, so there are challenges in that regard. So the uplink throughput is quite good when you are connected to 5G, and basically it gets lower, of course, when you need to transit to 4G due to also longer links. So these tests were done in Lannion in France, and the preliminary results of these indicate that the quality of experience within these kind of flights is at least as good as it's on the ground level, thanks to the line of sight radio communication propagation characteristics. So these are results at 120 meters elevated altitude and 50 meter altitude measured on the same, different days of course and at different times, but you can see that there is a lot of similarity, yet still somehow they are different. With regards to long-range power line inspection use case 3 scenario 1 sub scenario 2. So the apps developed for the scenario worked well. We did reach some of the KPI targets, but not all. We had issues with the uplink, for example. So there was a constraint in the University of Oulu, so that when we went to the botanical garden, the 5G standalone coverage was not, uplink signal quality was not good enough to connect to 5G. But on the parking lot that we did testing, there were, like, since we were flying heavy drones, it was not possible to actually fly the drones over there. So had to conduct the actual flight measurements in the botanical garden with the 4G, and that of course provides with an interesting understanding that 4G is not necessarily sufficient for these kind of operations, especially when you are using LiDAR. So search and rescue, similarly, it's a heavy drone, so we could not actually provide the actual flight in the parking lot where the standalone network coverage exists. So we had to go to the botanical garden and use the 4G base station. And there is about a kilometer or a bit less than a kilometer link distance from the base station to the cellular equipment, in addition to obstructing buildings, etc. So a lot of the actual required characteristics were able to be fulfilled, but the latency was not achieved with this operation. So when you're sending a video, the mean frame time needs to be less than 20 milliseconds. That was achieved even with the 4G connectivity, but the mean latency was too high. So there is room for improvement. So with regards to the situation awareness and UAV-based IoT data collection, so in terms of cloud resource consumption, it's been demonstrated that deployed services may not consume the same level of resources. It's been demonstrated the resource consumption of the service may evolve over time, and this needs to be taken into account. So we need to have customized cloud resource allocation for services running at the edge server, which is future work. And also you need to be able to scale the resources and services that evolve over time. This kind of UAV-based IoT data collection is actually a download or downlink-oriented process, which the current test facilities, the 5G facilities, typically they're downlink-oriented. So for IoT is actually operating often exactly the opposite. The same is actually for majority of the UAV operations that we tend to extensively use the uplink. And that's actually a clear limiting factor in majority of the use cases, that when we start using heavily the uplink, and if we extrapolate a bit to having more than a single UAV, the uplink capacity is quite easily saturated. So with regards to the IoT data collection, so you can see here some results on the evaluation of the upload speed and evaluation of the downlink speeds in the use case. Location in non-GPS environments. So it's a hot topic in the drone industry. So the project has spanned 4 years, or 3.5 years. So a lot of activities have happened on this topic, and especially camera-based indoor navigation has become a viable option as the algorithms have been investigated, and there are even some commercial off-the-shelf solutions now available. The measurement protocols and tools that we developed during this project, they are extremely valuable in the sense that it enables replication of replicating basically the results, and we can also replicate the measurements using commercial devices when we have the methodologies the results were not groundbreaking in this, but at least you can see that it's a viable option, and we can get a lot of data, and it enables tracking. Basically, we can see that the signal quality is quite passable or quite it's something that we can develop towards having a location of a user equipment in a non-GPS environment. Finally, the connectivity during crowded events, which is the use case scenario 1, so connectivity extension. So there was actually quite a lot of different measurement or test cases in here. I can only capture a few of them. So the measurements were collected using iPerf, for example, and we can see that there is actually even improvement in uplink when we have like Wi-Fi serving applications over the air. So with a 5G backhaul and respect to the situation where this such so I mean that the drone-based coverage extension is not used. There were a lot of test cases, as I said previously. So they were done in the Galileo Stadium. The tests were test case number 5 provided that there is a lot of stability with in the network when providing the service, and when providing the so when changing to a commercial 5G setup, we managed to actually attain the downlink rates of the 5G KPI targets. So we reached a maximum capacity of 1.4 gigabits per second, which is above the 5G KPI target. And the uplink rate was simultaneously around 90 megabits per second, which is quite good. So with good coverage, there are noticeable variation in the scale and range of measurements, and there were spikes which need to be further investigated. And it seems that from the UAV application perspective, so if we have downlink bit rates less than 15 megabits per second and uplink bit rates less than 10 megabits per second, they are in many cases sufficient for a drone session if we want to isolate drone-based services. So both optimized and non-optimized networks can effectively serve a lot of the drone operations. Of course, if we change the application payload of a drone, for example, the DRE to LiDAR, the situation changes quite a lot. But that's shortly the key takeaways. We will publish the deliverable 4.4 by the end of the project, which is next week, or at the end of the project, which is next week. So end of next week, the deliverable should be available on our public website. So thank you.
Thank you, Jussi. We are 10 minutes behind of schedule, but it was so interesting and so very good. Very good. I will mute Jussi because you give a lot of echo. So anyway, let's have a short Q&A session as well, and if anyone in the public or audience wants to ask a question, just open your mic and so on. But maybe I could kind of warming up the people first and asking. This goes probably to Jussi and Fofi as well. I think that is on the line that how many 5G KPIs would be kind of needing to be improved for drone purposes?
Jussi, will you start or?
I'll let you start.
Okay, so what is interesting from the trials that we have done is that the basic KPIs that the UAV people are interested to, and these are where they are building their trust to use the 5G technology at least, is the latency, and this is because that will allow them to operate 5G on beyond visual line of sight, let's say operations. The uplink, most basically because this is the service that the UAVs are actually considering, and imagine that an uplink in the definition of the UAV service corresponds actually to an uplink and downlink measurement, an aggregate value for the network, because actually an uplink in the UAV logic is actually uploading from the terminal to the network and then downloading from the network to the application. So it is let's say a complex operation from the network perspective. And obviously, very importantly, the service creation time, and this is because we see that we are going to reach to a plateau of a dynamic provisioning of these services so that to actually respond to the need of the UAV service in a reliable way. So I would cherry pick these three, and I would say that we have seen that there is a distance between what the network is actually measuring and what the application perceives. So we need to see the full stack. As noted before, there are various complexities that are coming from the security channels, the VPNs, and whatever other layers that are imposed. It was very important that we have seen that the edge of loading is working and can provide some kind of a localization of the service to actually optimize these KPIs. But I would stick to this, and I will say that also what the project has found is of importance is obviously the capability of getting a dedicated network slice for the UAV operation, so that to avoid any undeterministic, let's say, behavior of the network. And I think this was the most important finding, because overall we have seen that for scarce operations of UAVs, it is not a performance issue for the network side. It is mainly a reliability and robustness issue, which is actually satisfied by the release 1617 capabilities that we are expecting from the networks. So Jussi, this is on you now. You need to add something.
You were quite quite extensive. So one thing I want to point out in here that the current generation mobile user equipment are a challenge because they provide a drastic difference in terms of performance, especially if you start looking at uplink and downlink performances. So at the University of Oulu, we tested 4 different mobile handsets and at least 2 different modems, and they all provide quite drastically different uplink and downlink throughputs. The latency is quite I mean similar in most of the devices, but in order to, especially for considering UAV operations, you probably want to investigate which are the modems that work best for the application, because we can see drastic differences in, for example, since at the University of Oulu we have 60 megahertz of bandwidth for our 5G, so we can attain downlink capacities of about 500 megabits per second, but when you change to another handset, it drops to 200 megabits per second, and then basically all of the other modems and user equipment, they provide something in between. Then actually it's often often that the terminals that have very good downlink throughput, their uplink throughput is really bad, and vice versa. So some care needs to be taken into deciding what is the user equipment that you're going to adapt to your device or to your UAV.
Thanks, Jussi. So it's probably so that basically in the commercial 5G networks, then it might be a kind of challenges in a way that you test it with one network and it seems to be working perfectly, and then you change to another one or go to the other country, then you are having problems. Boris, you was the first one lifting the hand, so please open the mic. And I see that Barbara was sending a message as well.
Yes, thank you. Boris Resnik, CTO for Flyversity. Considering there are several activities ongoing that are trying to standardize cellular communications for drones, it was identified that a key question for this standardization is a mapping between KPIs that were considered extensively, as I see in this project, and aviation-defined requirements for the data links. And the question is, did you investigate into aviation requirements? Especially this applies to continuity of the service, which looks like as something that is not directly addressed by conventional telecom KPIs. Thank you.
Who wants to take that?
Okay, I will give it a go because I think that it is true that mapping the aviation KPIs has been a puzzle for the project. Mainly, the approach has been to start off with some, let's say, more empirical requirements coming from the UAV business and the use cases. It has come to the trials as a realization on what has been the practical evaluation from the use cases. But I think that I don't know if there has been some work on the standardization board, but this mapping that you refer to has not been part of the exercise on the KPI definitions that we have actually worked in the project. True. What we see is that the network KPIs in respect to the reliability that you refer to have been, let's say, on the background studied because we have a couple of use cases that have actually been looking into a handover impact, for example, a large scale of flights which does not directly, let's say, contain the target KPI of the aviation business, but it still addresses the reliability concern that you are raising. And there are some results on how we believe that the service can actually be reliably provided through this kind of handovers. And even we have actually seen this in commercial networks. For example, I can refer to the experience that we had in the Cosmote Stadium, that we in the Cosmote network using the flight over the commercial open air network, where we have seen that to cut the long story short, if we can survive if you can have a slice that is dedicated to the UAV service, the handovers as a technical mechanism from the network are not actually disrupting the service of the UAVs. It is the signal strength and the ability of the UAV to always get hold of the service, of the 5G service, that is going to actually make a difference to the operation of the UAV, and not the technical handover, let's say, process that is a little bit, as Jussi has said, is a little bit transparent to the application and is related to the UE capabilities. Obviously, the key thing is that we are actually discussing about solutions that are still experimental. So we have not seen a slicing at the enterprise level, so it's not very easy to perform field trials with these solutions, but to conclude, even though we have not actually targeted the UAV KPI, the aviation KPIs, we have still seen into the reliability through some of the use cases that we have tried.
Thank you, Fabi, once again. Barbara was sending a question, actually two questions. The first one is that the measurement that you did were on the network or on the UI also, or UE also. You just mentioned that you noticed a big difference in the UIs. Would the report indicate some learnings, successions for UI2? Maybe Jussi, you can.
Yes. So I mean, so we did for the University of Oulu test, we used a Cosium measurement tool, so which enables us to put probes in different points of the network, so to user equipment, to the core, to the edge server, and essentially any place where basically you can run Linux or operating system, for example. So it's kind of difficult to state. So what would be the lessons learned from the UE perspective? So it's kind of difficult to start making recommendations that you should use this device and not that device.
Jussi, maybe I can tell you.
Yep.
I'm not looking for recommendations or which one is better. Is more looking, as you mentioned, maybe they handle better the handover of frequencies, or maybe the power, or generic recommendation that you notice that are maybe characteristics of some manufacturer, but I don't want to know, crack that performs better than another one, or vice versa. No, because I can definitely understand you can't do that, but maybe give some indications of the UE should be careful to maybe not do that, or recommend to do that. In that sense, I meant.
Well, it seems that at least at the moment, the UEs don't recover very well if they suddenly drop out. So oftentimes you have to manually, but of course that might be specific to our particular network. But since we have some specific modifications we need to make on devices so that some of them work, because we are not a public service provider, so many of the user equipment, they have service provider lists that do not enable the basically connection out of the box. So when we need to have them modified so that they suit our network, you may that basically you lose some of this automated reconnectivity process. But you can see that especially if you have both standalone and non-standalone network operational at the same time, and you have a connectivity drop, then basically when the mobile phones recover, they automatically jump onto the 4G anchor back then to non-standalone, and at least in our network they don't recover, they don't go back to standalone.
Got it.
But of course, that's like when you are fixed to an operator, probably does not run non-standalone and standalone network simultaneously. So that's probably not a problem in commercial urban environment.
It will get, but that's good to know.
So I don't.
Sorry, Jussi, I muted you. there is a coming so bad echo, so I muted you and I realized that you just started to speaking. So open your mic again.
Yeah, I don't know whether it answered Barbara's question.
Yeah, no, absolutely. So as a note, obviously from the GSMA side, we also have to give recommendation or do some test of certain behavior on the UE. Hence my question. So if you notice certain behavior, then we can put also into GVP some specific questions on, data behave like this rather than that. But as you mentioned, obviously, yes, right now, because most of this deployment is non-standalone, I presume the algorithm will pull back and go non-standalone immediately. But as you mentioned, if you lose the connectivity, it doesn't recover, then it maybe is the investigation to figure it out what they're doing in that sense. So to try to see how to perform better. That's what was but you answer. So thank you very much for that.
Thank you, Barbara. Thank you, Jussi, for good answer as well. I think that we take the last question, and Barbara, I will jump your second question, and we go for Oula was sending in the chat the question. Do you want to, Oula, say it in the mic? Well, I can. So Ola was asking that. So based on your findings, do you identify the need for service capability measurement for KPIs, 4G or 5G of airspace, say to 10 to 200 meters before implementing actual drone services? Who wants to take this?
Okay, now if I am allowed to comment something here, I think that I don't know how useful it will be to actually just before to know the real-time KPI measures before executing the flight. So what it is definitely one of the key takeaways for one of the use cases has been that the UAV application should know so that to adapt. So in this perspective, it is not for me the same thing, because what we are saying here is that have the reflective capability in the application level, for example, to use adaptive bit rates in the video streaming when they are actually seeing that the signal strength of the network during the operation of the flight is degrading. So obviously another thing that has been a common denominator of all the use cases, that the careful planning of the radio coverage in the area where we know that we are operating before. So pointing the antennas, tilting the antennas to the proper, let's say, height where we expect to have the operation. Or even extending the coverage to some places that we see that the coverage is not good, or using equipment in the drone that is always having line of sight with the antennas and the GNOPs that are serving the UAVs. Some kind of this preparation and cartography of the flight plan in cooperation with the 5G provider will definitely ensure that we have a robustness to very high signal strengths, because it is the signal strength that is actually, in essence, defining what will be the KPIs and what will be the coverage and the connectivity experience that the drone is going to actually enjoy. So yes, the UAV should be aware of the network capabilities when they are on the field. Not all the KPIs, definitely the signal strength, and it would be advantageous if it onboarded the intelligence to adapt using the automation and the intelligence that they already have in some, let's say, non-deterministic situations that can always appear. So Jussi, I don't know if you want to say something more here.
Yeah, actually, I want to compliment that, because whenever you operate the drone in a cellular environment, 5G especially, you don't know what type of antenna the service provider is using and to where it's tilting. So it may be that your service provider has an antenna that basically is vertically very narrowly aligned. So when you reach the altitudes of, let's say, higher than 50 meters, your actual coverage that you can get is, and especially the SNR, may vary like from 1 meter to another very heavily, because you're essentially trusting to side lobes for getting the coverage. So definitely, I really like support what Fofi said before, that basically you would need to have the drones be able to monitor what's the SNR of the signal and adapt to that, because when you go above the antenna beam height, you are in, let's say, adventure zone, in the sense that you don't know exactly what kind of service you're going to get. And of course, it will take some time before the antenna, like antennas used in public telco networks will have the ability to track a drone, so provide that kind of a service. I mean, as part of in addition to getting a slice, for example, to actually provide an antenna beam of good service based on the flight plan. So that's probably quite a lot of time in the future, if even then.
Good, thank you. Well, I think that we'll close the webinar. We are just only 23 minutes late, but it was very good discussions, very good questions, and very good answers. So Jussi, Ludwig, Harilaos, Karim, Jussi again, Hamed, Pascal, Tanel, Pascal again, and Fofi for excellent answers. Thank you for being presenters in the webinar, and yeah. So I would say that we call off for the webinar.
So thank you very much.
Yep.
Thank you.
Thank you.
Thank you.
Goodbye.
Thank you.
Thank you. Goodbye.
Thank you. Goodbye.
Bye bye.
Bye bye.